So this is Math 270, and this is week 3, where we're going to look at 6th grade geometry standards. I should have the PDFs in each of your modules so you can, the standards, so you can always look back. Maybe you've already printed those, put those in a notebook or something, or at least bookmark them on a web browser just to know where you could find those. But these would be your standards for 6th grade in regard to geometry. So just a little bit of review, thinking about the shapes when we were talking about 5th grade. Do some, let's say, let me add a few things in here. So let's say this is one length, this is another length, and this is a third length. So given that triangle with 3 different lengths, we would call that a scalene right triangle. Scalene meaning all 3 sides are different. It has a right angle, so we would call it scalene right. Here we have a general rectangle, also known as a parallelogram, and it's a quadrilateral. Here we have a parallelogram, and it's also a quadrilateral. And this would be a trapezoid. Also a quadrilateral. And then let's say that, well, if we had 2 sides that were the same, then we would call that an isosceles. But if we had 3 sides the same, we would call it an equilateral. So those are just some review of some shapes. But now with 6G1, we're looking for finding area. So when we're dealing with area of triangles or quadrilaterals or different polygons, we need a formula to do that. And those are some general formulas that I'm sure will recall to you as we talk about this, but we just want to go through where the formulas come from. So we're just looking strictly at deriving those. So when we look at a parallelogram, well, parallelogram, remember, could be here we've got a 4 by 4. So the area inside that, you're thinking about the units, the unit cubes, or the unit squares, that are inside there, and we would say that that is 16 square units. I would have to say 16 square units. Now that would be finding the, for a parallelogram, to find that area, we would say the length times the width, because that's what we would say, 4 times 4. And we could do the same as what if we were looking at a rectangle. And if this was a 1, 2, 3, so that's a 4 by 8, then we could count all the square tiles inside there. And so that would give us 32 square units. So those are different parallelograms. Now we also have a parallelogram that may look a little different. In this shape. Well, we are still looking for the area inside, and we can count the base here, but we're kind of figuring, well, what's the height on this? Okay. Well, if we have this shape, there's a couple things that we could do. We could look at dropping this down here. And if I cut this triangle right here, and I placed it here, then what we would see is a 2 by 4 rectangle. If I just chopped that triangle off, placed it on the other end, this is what we would see. So we really have a 4 by 2. Now, if I'm going to erase and kind of go back over here and look and see, originally I do have a base of 4, but if I'm looking at my altitude here, this height, that height is 2. So if I multiply for the parallelogram, the area could be the base times the height. So it's still going to be 8. It'll be 4 by 2 to give me 8. Over here, I see the base is 4. I see the height is 2. I still get an area of 8 square units. So it's this one here that people tend to look at and wonder, well, can I still use base times height? And the answer is yes. I just need to figure out my height of that parallelogram. So those are all different different shapes, but we're still looking at the formula for a parallelogram as length times width, or base times height. Now, if we take a square like we have, and I draw a diagonal, I already know that this area is 16 square units. If I draw the diagonal, I have cut the area in half to give me 8 square units. So what we can say with the triangle is that it is the same as the length times width, or a base times height. We just need to make sure that we take half. And this is a very common mistake amongst sixth graders, is they've been almost ingrained with finding the area as a base times height, the base times height. And then with the triangle, they still do the base times height and they forget to divide by 2. So that's something that's very common with that age group. Finally, let's look at the trapezoid. Now, trapezoid, I'm going to look at the parallelogram example in addition to proving this formula. Okay, so this formula is actually A equals 1/2 base 1 plus base 2 times the height. So we're going to talk about where those pieces come from. So if I'm just going to draw the height is 4. And I'm going to make this trapezoid. So I know that this is 6 units, and this top, what we'll call the top base, is 3 units, and the height is 4 units. Now this is a slant height. We don't know that, and students have a couple of years to find that slant height, which comes when they are studying 8th grade and the Pythagorean theorem comes into play. But at this point, they're not learning how to figure out a slant height. So this is your area of a trapezoid. So we're just trying to prove this formula. So if we know this is 3 by 6, so what I want to do is I just want to invert this. And I want to draw just a mirror of it so that they're connected. So the one in red, we see this area. Well, the trapezoid in red has this area. So they have the same areas. But what have we created? We've created a parallelogram. So this length is 3, and this length is 6, and this length is height. So what is the base? Well, the base is 6 plus 3. And the height is 4. But what that would give me is 9 times 4, which is 36 square units. And I don't want the entire figure, remember? I only want this one. So what does that mean that we would do? We would take half of it. Hence, here's where your formula comes. 1/2 base 1 plus base 2 times the height. So next question. So Brittany and Sid were both asked to draw the heights of parallelograms. Look at their answers below. So notice Brittany said, well, I want to draw the height over here. And Sid says, well, he wants to draw the height over here. Could there be another way to draw this to figure the height? And the answer is yes. You could go outside of the trapezoid and drop your altitude over here. So this would be another way to find the height. But are both Sid and Brittany correct? Yes, they're both correct. You can place that altitude at any point inside that trapezoid as long as you are creating a 90-degree angle to the base. Number 4, do the rectangle and the parallelogram have the same area? So here's the rectangle, which we know is going to be base times height. Here's our parallelogram, which we know is going to be base times height. And we know that based on some of the previous deriving those formulas, and you can go back and look at that again. But with the rectangle, that area is going to be 15 multiplied by 8. And the parallelogram is going to be base, which is 15, but notice where the height is drawn. It's going to be 15 by 8. So 8 times 10 is 80. 8 times 5 is 40. So we've got 120 square feet as the area of the rectangle. And then over here, we've got 8 times 10, which is 80. 8 times 5 is 40. We have 120 square feet as the area of the parallelogram. So yes, they both have the same. Because those are two different ways to draw the parallelogram, but they're both parallelograms. So they both are going to have the same base times height. But notice you've got that 10 foot, that's that slant height, which a lot of students make that mistake of saying 15 times 10, which would give you 150, and they would say that the areas are different. But remember, you're not using that slant height of 10, you're using that height of 8. All right, and then number 5, what if we said that a parallelogram had an area of 20 3/10 centimeters squared and had a base of 2.5, what would be the height? So with your equation here, you're trying to solve for the height, and you see that it's 2.5 times the height, then we can divide both sides by 2.5. This is still a year where it's kind of that teacher discretion of when you're going to allow them to use a calculator or not. And there's a lot of argument about that amongst teachers and kind of when that break. I will tell you that I encourage all of my sixth graders to do as much as they can manually by hand. And when they hit seventh grade, there's a whole lot more calculations involved, so we use the calculator to do that. Now, I also use my discretion with my sixth graders when they're working with problems that division of decimals is pretty hefty, then I'll allow them to use a calculator to show me that result. I don't want them doing long division up to 6 decimal places because it's kind of tedious after that. But something like this, 2.5, how many times will 2.5 divide 20 3/10? Well, remember, just a review with division of decimals, you'd like to have that divisor be a whole number. So I'm just going to multiply 2.5 times 10 to make it 25. And I'm going to multiply 20 3/10 by 10 as well to make it 203. And notice where the decimal point's placed. So 25 would divide 203 8 times. That would be 200. 25 will divide 3, not a whole amount of times, but 1/10 times. And then 25 would divide 50 hundredths, be 200th times. And you get a remainder of 0, which means that's just the indicator that it's going to terminate. It'll have a terminating decimal. So what's the height in this case? It'd be 8 12 centimeters. Task number 2, where we're finding areas of polygons. This is where, when you have the coordinate plane, you're asking students to look for different types of shapes to help them find the area. So if they recognize a square, if they recognize a rectangle or a triangle or a parallelogram or a trapezoid, they're looking for those shapes so they can subdivide that shape into something they know. When you look at some of these irregular shapes, we don't have a formula for that shape. We don't have a formula for this shape. So when I say a couple of different ways, how could you find the area in different ways? Well, a lot of times it's just what you see. So for instance, what if a student sees, well, I'm going to subdivide it here and here. So I know this is 1 square unit. This is a 1 by 2. That's a rectangle. And here's another rectangle. That's a 2 by 5, which would be 10. Now, certainly the students can count these because they can see it, and they can count, and they would see that that's 10, 2, and 1. That would be 13 square units. That would be one way. Now, erase that, and let's look at another way. Another way would be to enclose it. And you can do this method for all of your figures. And you're just trying to figure out what's the area of the entire figure. Okay, so once I enclose it, I see that this is a 1, 2, 3, 4 by 1, 2, 3, 4, 5. So that is 20 square units total. But what I need to do is subtract all of these additional pieces here. So the top one is 3, so I'll subtract 3, so that'll give me 17. I've got another 3, and that'll give me 14. And then I've got one more to subtract, and that would give me 13 square units. So I'm just kind of subtracting all the pieces in yellow. And we'll do that for these next 4 shapes. On the one on the right here, I'm looking at this one, and I can see, well, that would be a triangle, and that would be a triangle, and another triangle, and all of these were, I see a triangle here. And so this is one way to look at all these half. Well, these 2 would make 1. These 2 would make 1. These 2 would make 1. So all those make one whole unit. And then I have a rectangle here of 2. I have a rectangle here of 2. This would be 1. This would be 6, and this would be 1. So total, I would have 6, 7, 8, 9. So 6, 7, 8, 9, 10, 12 inside. And then you see the ones on the outside where I've kind of pieced those half triangles together to give me 15 square units. So that's just subdividing it up. Now, I can also see some trapezoids in there, some rectangles. So it's really whatever the students want to use and whatever they see. Or you can subdivide it. Excuse me, I just did subdivide it. Now I'm going to enclose it. And I want to subtract all these pieces after I found the total area. So this is going to be a 4 by 5. So there's my 20 square units. So I'm going to subtract this one off first. And so that's a 1 by 1. And I got to take half of it, so that'd be half. So I'm going to subtract those two to make 1. So that's 19. And then this one here is a 2 by 2 triangle. This one's a 2 by 2 triangle. Well, the 2 by 2 is 4, but take half, this is going to be 2, and this is going to be 2, which is a total of 4. So if I subtract that, I get my 15 square units. So again, one way is to subdivide it. Another way would be to enclose it and subtract the pieces away. With this one, I see a triangle here and here. So this would be a 1, 2, 3, 4 by 2. And 4 times 2 is 8, and cut 8 in half. So that would be 4. And then this one would be 4. So that would be a total of 8 square units. You can also enclose it. And then remember to subtract all these pieces away from it. So this is going to be 4, and this would be 4. And this is a 1, 2, 3, 4 by 2. So that's 8. So this will be 4. And this would be 4. So you're actually subtracting 16 away from something. Well, this is going to be a 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So that's going to be 24. 24 take away 16, and we get 8. Now, so far, these first 3 have been, I'd say, an easier subdivide. You've been able to look at it, divide the pieces up into shapes that you know. Then you get to this one here. And no matter way you look at it, you really can't subdivide this into triangles that meet at any of the crosshairs or rectangle or the squares or even rectangles. So really the best way to do this one is to subdivide, is to enclose it instead of subdivide it. And when you do that, you're going to see it's a whole lot easier to calculate these triangles than it is to try to subdivide that into triangles and squares. All right, I need to know the length. So 1, 2, 3, 4, 5. 1, 2, 3, 4. So that's going to be a total of 20 square units. Now, what am I going to subtract away? Well, this triangle here is a 1, 2, 3, 4 by 1, which is 4. Take half of 4, that's 2. So I'm going to subtract 2. That'll give me 18. This one's a 1, 2, 3, 4, 5 by 2. That's 10. Half of 2, that's 5. So I'm going to subtract 5, so that'll give me 13. And this one's a 1, 2, 3, 4 by 2 is 8. And half of 8 is 4. So I'm going to subtract 4 from 13. And I get 9 square units for that different looking triangle, because it was really hard I wasn't given any heights or base or whatnot. So given on the coordinate plane, I have to try to subdivide that into what I can see. And the only thing I can really see is to just enclose it. Looking at the next task number 3, where we're looking at, we've got same bases and height, but we've got variations of it. So this task is just asking students to look at all of the different triangles that are given in the 4 figures. And so when you look at these, you can see that each of them have a base of AB, which that has a base of 1. But look at your height. Your height is 1, 2, 3. Your height is 4. So we would have 4 times 1, which is 4, but it's a triangle, so we have to take half, which would give us 2. So that would give us 2 square units for this one. And that you can see that vertical base, BC. That segment BC is vertical. But then when you come over here, you see AB still has a base of 1, but BD is now a slant height. Well, remember when we talked about the slant height, we can't count the dots to the side. We have to look at it as drawing that altitude. So that vertical piece right there is 4. And so the base is still 1, and the height is 4. So that's 4 times 1 is 4. Take half of 4. I'm going to get 2. So far, these have the same areas. I'm keeping the base the same on figure 3 and 4. I'm just changing my slant. I still have a base of 4. I still have a height of 4, and I still have a height of 4 here. So the base and the height is not changing on any of these triangles. It's just that slant. So in figure 1, AC has a different slant than AD and AE and AF, but the area of all 4 figures is still the same. It would be 2 square units. Another task where we look at the base and the height. So Mrs. Leto asked her students to label a base B and corresponding height H in the triangle shown. So she wants her students to label correctly what the base would be and what the height would be. So 3 of her students did the following. Sophie labeled this her base, and then this would be her height. And that height would be perpendicular to the base. Mark looked at it as it was originally in the one that she gave, Miss Leto gave. So Mark took that picture and he said, well, that's going to be the base, but then this is the height. Well, that should be a red flag right there because that is the slant height. And we cannot use that as a slant height. So Mark is incorrect. He would be correct in labeling the base. Remember, we would just need to bring that vertical piece there to create a height. And Mark didn't do that. Now, KK learned from Mark, and she did drop down a vertical height, but there's only that length, and she said that this entire length was the base. So KK is incorrect on that. If she would have just labeled, let me go back here. Remember, she labeled this entire piece as the base. But if she would have just labeled this section as the base and kept her idea of that height going vertical outside of that triangle to make that a 90-degree angle to that, she would have been correct. But KK was not with her original thought. Sophie has the correct idea with the base and the, so she's, if we turn Sophie's picture around, she's saying that this would be the base, and then she's dropping that altitude here to make that the height. This next one is a really good task that I've seen in class, and when I was an instructional facilitator, math coach, we did this several years. I was coach for 3 years, but when I watched teachers give this one, it was always so interesting how students solve this problem. And what we gave them, it was around that time where we had the oil spill off the Gulf. And so what we did is kind of, we took this problem that was created, and the president of the National Oceanic and Atmospheric Administration says, hey, I need some help with this. So it's basically as this president is reaching out to these students in class and say, I need your help to estimate this. So what they're basically doing, you can read through the task, basically asking the students, and you can give the students different options. They can look at an oil spill that looks like this, or they can so oil spill number 1 or oil spill number 2. It's really kind of let the kids choose what they wanted to work on. But based on what the students knew, they could either subdivide it or they could enclose it and, remember, subtract pieces out. So remember, this is strictly an estimation. So you might see kids that drew things like this, and I'm just estimating, right? So they see a parallelogram, or they see a triangle, and they see a triangle here. And this is a rectangle and a trapezoid, and this is a parallelogram, and this is a parallelogram. And here's a trapezoid, and here's a rectangle and a rectangle and a triangle and another rectangle and a parallelogram. So remember, what you're trying to do is just give some estimates. It's okay if it doesn't catch everything, but what you're looking at is, let me find the area of these pieces. So what we did is we even encouraged the students to try it, but then try to, here, what did I have? I had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I had 13 shapes. We encouraged the students, what if you get less than 13 shapes? And so we had several runoff copies of this, and we just wanted the students to think maybe bigger shapes or different shapes, or but anyway, what we have is that 1 centimeter is equal to 2 miles. So we were having the students use centimeter rulers and figure out, they would figure out the area. So when the students are doing this, they may take number 1 here, and it might be that the length is 7 centimeters. Well, remember, they can change that into miles, because they know that for every 2 miles, it's 1 centimeter. So then that would give them the 14 miles. So we would say that maybe that they just converted to that's 14 miles. And let's say the height is 6. And so now 6 centimeters times 2 miles per 1 centimeter is 12 miles as their height. So now they would do 12 by 14 to figure out that area. And so they would do that. They would find that area 13 times, and so they could give that president of the Oceanic Administration an estimate of how much. Now, it's certainly just a quick estimate, and that's what we're asking the students to do. That's just one way. I mean, they could, if you you could also measure what if that first one like I said, number one was a 7 centimeter by 6 centimeter. Well, that would be 42 square centimeters, right? If that was your height. Well, they can also square this and make it one square centimeter would be 4 square miles. So now you're multiplying this 4 square miles and 1 square centimeter. So now it's 42 times 4, and you would get 168 square miles. Well, that would be the same thing that you found if you multiplied 14 and 12. So anyway, that is one way to look at that. Of course, you could have the students enclose it and then look at how they can figure out different shapes to subtract. So really interesting activity for the students. And then they just find all those pieces, but then they subtract out after they figure out what their length and what their width would be using centimeters. 1 centimeter equals 2 square miles. So I would encourage you to use that activity if you happen to be working with 6th grade. They enjoyed it, and we definitely gave them plenty of time to work on that. It's certainly not something you can do in one class period. So our next activity is looking at polygons in the coordinate plane. So this one incorporates 6.1 and 6.g.3 and 6.g.1. So you can see the standards that it would incorporate. But now we are plotting polygons in the coordinate plane. So what we're going to do is and this is something where you have the notes in front of you, you can pause the video and you can go ahead and plot these on your coordinate plane that you have. And so we should have 8 of those pictures, and they should not overlap the way I've set that up. So they should all be in different sections of the coordinate plane. So let's look at the first one. So if we're looking at polygon A, I need to go to the left 7 and up 4, to the left 8 and up 5, to the left 8 up 6, to the left 7 up 7, to the left 5 up 7, to the left 5 up 5, and then back to -7, 4. So now I can just go ahead and use my straight edge, and I can circle that in. And then what we would do is ask the students to go ahead and, once they plot them, to go ahead and subdivide that and find that area. All right, so that would be part A. So let's look at B, the second polygon. So that would be to the left 2, down 7, to the left 1, down 4, to the right 3, down 1, to the right 6, down 7, and then back to the left 2, down 7, so we can connect these pieces. So I'll just kind of keep changing colors here. So just ask the students to subdivide that how they see fit, or they can enclose it to find that area. All right, so I'm going to put, and I'll just go ahead and label that B. You have enough room on your coordinate plane, but I'm just going to switch screens just so they don't get all jumbled up in the video. So part C, I want to go to the right 4 up 3. And then go to the right 3 up 3. To the right 2 up 2. To the right 2 up 1. To the right 3 and 0. That's what we call an x-intercept. To the right 4 and 0 is another x-intercept. To the right 5 up 1. To the right 5 up 2. And then we're back to 4, 3. So there's an octagon, eight-sided, and that would be figure C. All right, in figure D, we want to go 0 on the x and down 10. That's what we call a y-intercept. And then we're at 0, -8. There's another y-intercept. And then we want to go to the right 7 down 10. And then we're back to 0, -10. So we have a triangle. We just count the base, count the height, and we'll figure out our area. And so I'll let you go ahead and compute those areas on your own. Next, we'll look at E. So that's to the left 8, down 5. To the left 8, down 8. To the left 5, down 8. To the left 5, down 5. And then back to -8, -5. So we have a 3 by 3 square. And that's part E. And let's look at F. So we're going to go to the right 9 and down 1. And then to the right 6 up 1. To the right 6 down 3. And then to the right 9 down 1. So we've got another triangle. And you can look at the base being here, and you could look at your height this way to figure out that area. And so that was figure F. And now let's go to G. So G would be to the left 6, down 4, to the left 6 up 1, to the left 9 up 1, to the left 9 down 4, to the left 6 down 4. So we have a rectangle, and that is base times height, or length times width, same as you would find the area of a square or parallelogram. So this was figure G. And then we're looking at H is -5, to the left 5 up 1, to the left 3 down 3, to the left 1 down 2, 0, 3. So there's a y-intercept. Next to the left 3 up 3, and then back to the left 5 up 1. So we have a 5-sided figure. So we've got that pentagon that's not regular. Regular just means that all the sides would be the same. And so that would be figure H. So again, different polygons in the coordinate plane Now we're working in all quadrants. Remember, or if you'll remember, 5th grade was only quadrant 1. Well, 6th grade brings in all of the 4 quadrants. And sometimes vertices will end up being on intercepts. So if it's an x-intercept, just means that the point is on the x-axis. If it's a y-intercept, it's on the y-axis. Those are good vocabulary to discuss at that time. And so this would be just practice with that, and also practice finding the area of the shapes. And then finally, we have task 7. This will be our last task to look at in part 1 of this video series. So I want to look at the prism down below, and notice there's a difference in the volume in 6th grade as there is in 5th. In 6th grade, you're going to start to see length, width, and height, the side lengths of a prism with fractional pieces. So now they're not just whole numbers as length, width, and height, but we may have fractional parts. So in order to calculate the volume, we're looking at the length times the width times the height. And so that length is 5 1/3. Well, let's go ahead and change that 5 1/3 from a mixed number that it is now into an improper. So there's 3 thirds in 1 whole. So how many thirds in 5 wholes? That would be 15. Plus the 1/3 that you see, that would be 16 thirds. The width, we'll say, is 2 thirds. And the height, we'll say, is 1 1/3, which is the same as 4 thirds. And so when you multiply this out, you're going to get 27, 3 times 3 times 3. And in the numerator, you're going to get 16 times 8, which is 128. And this is all centimeters, so we're looking at cubic. So now we're making the shift to cubic measurements instead of square measurements with the 2-dimensional. So everything on the coordinate plane, anytime you're talking about area, you're dealing with square units. Anytime you're dealing with volume, you're dealing with cubic, because you've got your 3 dimensions, your length, your width, and your height. So that would be your volume. Now, here's where there's a little difference, and we'll look at this in the next video as well. But what if you had to fill the prism with cubes that are side lengths that are less than 1 centimeter, less than 1 centimeter? What would be the best size to use? So when you're thinking of this, think about a length of a cube that would fit, right? This is what it's asking. How many of these would fit into here? Well, the best measurement would be a length, width, and height that are thirds. And so, well, because look at your length. Your length is 5 1/3. So it would make sense that we would use third measurements for everything to fit. And that would, if we were able to fill it, that's what we would think about, is that smaller cube being a third, a third, and a third, instead of, in 5th grade, they were looking at those cubes as a 1 by 1 by 1. And so when we look at that, relationship now, okay, well, if it's a third, if the small cube is a 1/3 by 1/3 by 1/3, then now you're looking at it's 1/27 cubic units. And so that relationship of the number of cubes to the volume, well, the volume can be found in one more way that I want to discuss with you. And here's that other way to look at that. When you know that this figure here is 5 1/3. Okay, well, think of it as that 16/3 that I talked about. Okay, well, how many 1/3 cubes could we fit into that length of 16/3? So with this division of fractions, right? 16/3 divided by 1/3, well, 3 divided by 3 is 1. 16 divided by 1 is 16. That length, there would be 16 cubes to fit along that side. So what we would see here is 16 cubes that are 1/3 in length to fit along their side. All right, what about the 2/3? Well, we would take the 2/3 and figure out how many 1/3 would fit in the 2/3, and that would be 2. So now we're looking at this being 2 cubes that are 1/3 in length or width to fit along there. And then finally, we've got the 1 1/3, which is the same as 4/3. And we would take 4/3 and figure out how many 1/3 cubes would fit, and that would be 4. So now we've got 16 times 2 times 4, but we've seen those numbers before, right? 16 times 2 times 4, we saw them right over here, which gave us 128. So the volume of the big prism was 128 cubic centimeters, but the volume of the small cube, which was 1/3 by 1/3 by 1/3, was 1/27. And so we wanted to divide that. That's what you would do. You would divide 27 into 128 to get that volume. So you can leave it as an improper, or you would get a little more than, around 4 7/10 as a volume if you looked at it through the division, if they did the long division. So we'll pick up with a problem like this called packing cubes, and we'll look at that in video 2. So this will conclude video 1 of the 6th grade geometry standards.